Hello, everyone. It is 8 a.m. Pacific time, 6 p.m. in Israel. Good morning, good afternoon, good evening, depends on your location. Welcome to this tinyML talk by the Israeli group. Today we have Dor Livne from DSP Group, who will be talking about PoPS, policy pruning and shrinking of deep reinforcement learning for edge devices. tinyML talks sponsors are ARM, tinyML strategic partner, DeepLight, Edge Impulse, Maxim Integrated, Kixo, Reality AI, and SynSense. We still have additional sponsorships available. If you're interested, please contact Betty at tinyml.org for more information. The next tinyML talk is going to take place on next week, December 22nd, by John Edwards from Sigma Numerics Limited. He will be talking about low MIPS and memory machine learning industrial vibration monitoring solution. It will start sharp on 8 a.m. Pacific time. If you're interested in holding a tinyML talk, please contact talks@tinyml.org. This is our first tinyML talk for the Israeli group. As of today, we have 230 members in the Israeli group. This group was initiated by DSP Group, and more companies are welcome to join. You may contact myself, Dor, or Tomer Malach in the email addresses listed here below. 2 sentences on DSP Group. So Dor and myself work for DSP Group, which is a leading vendor of SoCs, system on a chip, for voice applications. As of today, we have shipped more than 3.5 billion voice processors in different segments. Our expertise is ultra-low energy, sub-milliwatt SoCs for AI, machine learning, and other voice applications, which includes the SoC itself, as well as its firmware and the DSP algorithms. And you can see in this slide some of our customers that we are in mass production with. As of today, we've shipped more than 100 million SoCs specifically for the voice user interface application, and we're working with more than 40 different OEMs. So this talk is by Dor Livne from DSP Group. Dor has received his BSc degree in electrical engineering from the Ben Gurion University of the Negev in Beersheba, Israel in 2019. He's currently working on his master degree in electrical and computer engineering under the supervision of Dr. Kobi Cohen. His current research topics include cognitive radio, multi-agent deep reinforcement learning, neural network compression, and decision theory. And he works at DSP Group as a machine learning engineer. So without further ado, Dor, the stage is yours.
Thank you, Niv. So as Niv said, my name is Dor Livne, and I'm going to present to you a joint work of myself and my supervisor, Dr. Kobi Cohen. In this presentation, I'll present PoPS, which stands for Policy Pruning and Shrinking for Deep Reinforcement Learning, which is a novel compression algorithm which was recently accepted for publication in the IEEE Journal of Selected Topics in Signal Processing as a special issue on compact deep neural networks with industrial applications. So the outline for this presentation, we will first go over the motivation for compressing deep neural networks in deep reinforcement learning domain. Then we will present the reinforcement learning model and system and objectives. We'll briefly discuss existing deep neural networks compressing methods and why they don't work for the deep reinforcement learning domain. After that, we will dive into the PoPS algorithm and we'll explain it in depth and present the experimental results. So deep reinforcement learning uses deep neural networks to represent their policies, meaning the decision-making is implemented by the deep neural network. Deep neural networks are usually full of redundancy, which leads to redundant computations and memory usage. This redundancy prevents using deep neural networks on systems with limited hardware resources. Our motivation, the PoPS motivation, is to find a robust algorithm that can find an efficient presentation for deep neural network in the deep reinforcement learning domain, that can run on any normal hardware, meaning that they do not need any specialized hardware like other compressing algorithms need. So what is reinforcement learning? Okay, reinforcement learning can be summarized in this figure here. It consists of an agent that interacts with an environment by performing an action, the action AT. AT stands for the time step. And the agent performs the action AT with respect to the observable state, which is ST. After each action, the environment returns a feedback in the form of a reward and the next state of the environment. The agent's goal is to maximize the expected discounted reward. The name discounted stems from the gamma hyperparameter, which signals the emphasis on future rewards. If gamma is equal to 0, the emphasis is only on the immediate rewards. If gamma is close to 1, which is usually the case, there is more weight to long-term rewards. The policy pi, which projects from the state space to the action space, is usually represented by a deep neural network in the deep reinforcement learning domain. The problems we want to solve is one, there is a huge redundancy in deep neural networks, and secondly, is that existing compressing algorithms do not effectively apply in the deep reinforcement learning domain. The reason is that during the learning process in the reinforcement learning domain, the agent stumbles upon the infamous exploration versus exploitation dilemma. The dilemma is whether to use the action that has the best outcome so far, that is exploitation, or exploring new actions which might be better than the one we already know about, that is exploration. During the compression algorithm, which is a lossy compression algorithm such as pruning, the agent loses important information, and in order to recuperate, he needs to perform exploration again, which makes existing compressing algorithms which were developed for the supervised domain to fail. The contribution of PoPS is, first of all, developing a novel policy pruning and shrinking algorithm designed especially for the deep reinforcement learning domain while maintaining high performance. There's also an open source software that is available for researchers in this domain, and achieving the state-of-the-art performance in various challenging decision-making settings with respect to the size of the models that actually solve these decision-making environments. I'll now present some existing approaches, and we'll address why they fail and what is their disadvantages. So one of the main works in the topic of compressing deep neural networks is deep compression by Song-Hans. There are 3 steps in Song-Hans deep compression, that is pruning, quantization, and eventually Huffman coding. At the first step, there's pruning. Pruning is done, first of all, by training the weights in order to solve our problem. After we have a model that answers our demands, we prune the weights based on their magnitudes. We prune the small weights connection first, and after we prune those small weight connections, our model suffers from a degradation in performance. We then fine-tune the model and reiterate until until the model can no longer be pruned. The second step in Song-Hans deep compression work is quantization. Quantization is made by reducing the number of bits that represent each weight by distributing the weights to bins with k-means, also known as weight sharing. And the final step is that eventually Huffman encoding is performed on the quantized weight to save another 20 to 30%. Now, deep compression was tested in the supervised domain and outputs a sparse model which has 2 main issues. The first one is that there is an overhead representing sparse matrices, which is around 15.6% in memory storage. And the second problem, that in order to utilize the sparsity in the matrices, a specialized hardware is required that knows how to effectively perform calculations with sparse matrices. Now, this point is something that PoPS solves. He does not output a sparse neural network. He actually outputs a smaller architecture-wise. The number of weights in the compressed model is smaller than the initial model, than the uncompressed model, sorry. So before we dive into the PoPS algorithm, I just want to give you a little taste of what PoPS is capable of. So I give you this small and cute example, which is called the lunar lander environment. In the lunar lander environment, we have to land a spacecraft between the flags with minimal fuel usage. The state space is an 8-dimensional vector describing the spacecraft properties. The action space is 4 actions, whether to do nothing or fire main, right, or left engine. A successful landing yields 100 points, while crash landing yields minus 100 points. Of course, using fuel also yields negative rewards. The environment is deemed solved once an average of 200 points over 100 episodes is reached. The initial architecture has roughly 9,000 parameters. It was trained in an actor-critic fashion, which is a kind of a deep reinforcement learning training technique. I will not get into it. And after inserting this model, which was already pretty small, into the PoPS algorithm, PoPS outperformed the other baseline, which we will get to them later on in this presentation, by a landslide, and generated a compact representation of less than 0.8% of the initial actor representation, which is less than 100 parameters. Now note that that means that there's a model that is able. There's a model which has 66 parameters, which is able to solve the environment. I write a zoom. Because here is a little video of the lunar lander environment. This is the actual compressed model being used here. So you can see its performance. This is happening with only 66 parameters. It's a cute illustration of what PoPS is capable of. Of course, this environment, a model with 66 parameters trained from scratch using traditional reinforcement learning methods is not able to solve this environment using traditional actor-critic or any other traditional deep reinforcement learning techniques. Okay, I think that's summarized this part. So let's get into the PoPS algorithm in depth. So our proposed algorithm utilizes transfer learning to find an efficient, compact, and redundant free representation for the deep neural network while avoiding the exploitation versus exploration dilemma. PoPS outputs a compact model that is not composed of sparse matrices, as I mentioned earlier. PoPS can be divided into 4 major models. We will get into all of these 4 major models step by step. We will, at each step, describe the module. After we are done describing each module, we will plug it in its bird point of view to see how the entire PoPS algorithm utilizes these 4 modules to get the result that you saw in the previous slides. So the first 2 modules are quite small, so I like to present them together. The first module is training your teacher model however you like. The teacher model can be of any size, can be a large-scale redundant deep neural network. The only requirement is that the teacher will be able to solve the environment, which means that he satisfies our needs and answers our demands. After we are done training the teacher model, we will use the teacher to store batches of experiences in the experience replay, which is our second module. Experience is made of tuples that consist of state and the DNN output for that state, as can be seen here. These are the first two modules of the PoPS algorithm. Now we will get into the third module. Sorry. Okay, the third module is called the IPP, which stands for Iterative Policy Pruning. What's special in this module is that contrary to existing algorithms, there is no interaction between the pruned model and the environment. This bypass prevents the need to perform exploration. The IPP utilizes the experiences from the teacher via the experience replay, and the teacher keeps on interacting with the environment and feeds tuples of samples and their corresponding labels independently of the other modules. And this bypass, that we can see it right here, and we will see it in the macro point of view in a few slides, essentially circumvents the stability issue of the fine-tuning process by conducting it in a supervised learning manner. Now let's go over this module step by step. In the first step, we prune each layer by the following formula. This formula gradually prunes the model where GT is the sparsity demand at time step T, G initial is the initial sparsity of the layer, G final is the target sparsity, and T0 is the time step from which the algorithm starts to prune. The term N is the number of pruning steps to perform until GT reaches G final, and delta is the pruning frequency. This formula was established in Gupta's work to prune or not to prune, exploring the efficiency of pruning for model compression, which is available online and also is referred to in the full paper, in the full PoPS paper. Okay, in the next step in the IPP, which is the fine-tune step, which is the most important part, in the second step, we perform fine-tuning using policy distillation. In this stage, we use the experience stored in the experience replay, which is QIT is the output of the teacher, and the QIS is the pruned model's output for the for that corresponding state that we had in the experience tuple. The cost function is a variation of the Kubrick-Leibniz divergence, where the pruned model's objective is to mimic the teacher given a state. The third step in the IPP is to check convergence. If the sparsity converges and we cannot prune any more weights without harming the performance, we output the pruned model. Note that when I say harming the performance, I mean that the model can no longer solve the environment. From the macro point of view, in each iteration I, the IPP outputs a sparse model, which is able to solve the environment. In the fourth model, which we will present in the next slide, we will use that sparsity to create a new model. The fourth model creates a smaller model according to the sparsity ratios of each layer. After that, we train the model using the experience in the experience replay, and policy, and we use the same loss function, the policy distillation, until we get a trained dense model that is able to solve the environment. Okay, so in this module, we take this. We have a sparse model. We measure its redundancy per layer. We then create a model based on those redundancies, metrics, and statistics that we gathered, and we create a new model. And then we train it using policy distillation until he solves the environment. And that is how we shrink the model into a smaller architecture. After the shrinking model, we get a trained dense model. We then compare its size to the previous model. If the difference is smaller than a predefined threshold, the algorithm is done. And we output an efficient and dense representation of the deep reinforcement learning model. If it's larger than a predefined threshold, we reiterate from the IPP, when the IPP receives as input the compressed dense model in order to discover further redundancy. Okay, here's an overview over the entire PoPS module and algorithm. as presented in the paper. We train a teacher model. We'll go over it step by step to summarize all the 4 modules and how they connect with each other. So we train a teacher model however we like. It doesn't matter until the only thing that's important is that he solves the environment. The teacher is in charge of inserting tuples of states and their corresponding deep neural network output into the experience replay. Then the teacher or any other model is fed into the IPP. The IPP iteratively prunes the model while fine-tuning it using batches of experience from the experience replay. After the IPP can no longer detect any redundancy, the IPP outputs a sparse model, which is later fed to the shrinking module that creates a new compact model based on the redundancy discovered by the IPP and trains it using the experience replay to solve the environment. There are 2 usages for the same module, which is the experience replay. We repeat this process until one of 2 conditions are met. One, the size difference between the consecutive models is lower than a predefined threshold. In that part, we say we converge and we output we output the decompressed model. And second, the shrinking module cannot train the model to solve the environment. In both cases, Q output is the smallest model that can actually solve the environment. So we're now getting into the experiment section. So if there are questions regarding the PoPS algorithm, that might be a good time.
Yeah, let's take a couple of questions. So first question is, why existing compression algorithms do not effectively apply to the DRL domain?
Existing pruning algorithms completely ignore the exploration phase in the deep reinforcement learning domain. When you use these lossy compression algorithms in the supervised domain, you can fine-tune your model based on the labels, but that's not the case in the reinforcement learning. The labels in deep reinforcement learning are created by the model. So when you prune the model, you lose important information regarding the policy that you already learned, and in order to recuperate from that loss, you have to reinitialize an exploration phase in order to get that experience again. I like to think about it as kind of like a fog of war. So when you prune the model, the fog of war covers more ground, and then you have to rediscover it again. In order to rediscover it, you have to perform exploration again, and that destabilize the compression algorithm, which we will see in the experiment section.
Okay, and a second question, what exactly is different from the standard pruning to the IPP module?
Well, as I said in the last question, the main difference is that standard pruning techniques use traditional reinforcement learning methods to fine-tune the model when using lossy compression. And as I said before, for the same reasons, that harms the performance of these compression algorithms, because you again need to explore, you again need to put your model back into an exploration phase, and that harms the stability of these algorithms. So that is that's the main difference between the other between standard pruning and the IPP, is that the keyword here is transfer learning. Okay, so can I continue, or are there any more questions?
No, let's continue.
Okay, great. So in the experimental section, we will present a couple of experiments. One of them you already saw, which was the lunar lander. In this experiment, I will compare the standard pruning mechanism, which uses the same formula as the IPP, which is called MBGP. The MBGP uses traditional reinforcement learning methods in order to fine-tune the model, and the IPP uses transfer learning, as I said before. So the IPP's pruning mechanism is critical because it is responsible for finding the redundancy at each iteration. It is like our compass in the architecture space. And as you can see from the graph here, the IPP is a lot more stable and better than the standard pruning algorithm, which is the MBGP that I already introduced. The reason is that we use a teacher model that cuts the need for the interaction between the pruned model and the environment, thus avoiding the need for exploration during the fine-tune phase in the pruning paradigm. Okay, is this experiment clear? What it shows us? Okay. Let's go ahead. So the following experiment is called the environment experiment. It can be divided into 3 sub-experiments that show the superiority of PoPS to existing pruning-based compressing algorithms using 3 different models from the reinforcement learning domain that work on 3 different environments. One of them, the lunar lander, you already saw at the start of the presentation, so we'll not go over it again. The existing pruning-based compressing algorithms, which serve as our baselines in these experiments, are the magnitude-based gradual pruning, which I already introduced. It is the vanilla version of pruning, where the fine-tune phase is done with traditional reinforcement learning methods, and knowledge distillation-based pruning, where the fine-tune phase utilizes the teacher, but the experience is fed by the pruned model and not by the teacher. Okay, so that's a critical part to understand what is the difference between the knowledge distillation-based pruning between the IPP. The only difference is that the model that feeds the experiences into the experience replay is the pruned model and not the teacher as in the IPP module. Okay, so let's get into the first experiment. The first experiment is the cart pool environment. In this environment, we need to keep the pole steady. The state contains properties that describe the physical state of the cart and the pole. The action state space is pretty small. You either push the cart left or push the cart right. At each time step where the pole remains upright, the agent receives a reward of +1. The environment is deemed solved once an average of 195 over 100 episodes is reached. The initial architecture, The initial architecture is a feed-forward, fully connected layer with roughly 100,000 parameters. It was trained using a target DQN, and after inserting the trained teacher model into all 3 algorithms, which is PoPS, MBGP, and KDBP, MBGP is magnitude-based gradual pruning, where the fine-tune phase is done with traditional reinforcement learning methods. KDBP is knowledge distillation-based pruning, where the only difference between it and the PoPS algorithm is that we actually use the pruned model to feed the experiences into the experience replay. Okay, so after inserting the trained teacher model into all 3 algorithms, we can see from the table, that PoPS outperforms the other baseline and manages to generate a compact representation of less than 0.3% of the initial DQN representation. That's a network with less than 250 parameters that is able to solve this environment. Okay, now the following experiment is the Pong environment. The objective here is, I guess all of us know what is the objective in the Pong environment. The objective is to beat the computer and be the first one to get to 21 points. The state space are 4 grayscaled frames of size 84 over 84 stacked together on top of each other. They are stacked over one another to give the agent the notion of movement. Those 4 grayscaled frames are 4 consecutive frames over the time domain. The action space is also simple in this part. We either push the pad up or down, or we put it in play. We don't do anything. That's also an action to stay. A reward of +1 is gained for passing the ball behind the opponent's pad, and the reward of -1 is received when the ball passes the player's pad. The environment is deemed solved once an average of 18 points over 100 episodes is reached. Sorry, okay. The initial architecture in this experiment is a convolutional neural network with roughly 1.6 million parameters. trained using a target DQN and a prioritized experience replay. PoPS generated a compact representation of less than 1% of the initial size, while the other baselines did not manage to compress further than 20%, more than 20% of the initial model size. These experiments show that PoPS is able to deal not just with fully connected layers, but also with a convolutional layers. Also, this shows that PoPS is able to compress considerably at one iteration, as can be seen at the first step. We compressed around 85% at the first step. Note that PoPS is able to compress large networks as well as small networks, as we saw in the lunar lander environment, where we had a model that was only 9,000 parameters, which is already considered small. PoPS can be crude or delicate when the need arises. The size of the compression in each step is set by the IPP module, which is in charge of detecting the redundancy in the model at each iteration in the PoPS algorithm. The job of the IPP module, as I like to think about it, is to be a compass in the enormous architecture space and guide us in each step to the next architecture design. So thank you very much. That was my joint work over the algorithm PoPS. It was the joint work of myself and my supervisor, Dr. Kobi Cohen. There's a link here to the paper and a link to the source code. And if there are any further questions, I'll be happy to oblige.
Thank you, Dor, for this interesting talk. I want to encourage the audience here to answer the poll. And we still have at least 3 questions in the Q&A bar. So first question is regarding the lunar lander. The question is, how does the algorithm work in a 3D landing? Again? How does the algorithm work in 3D landing?
In 3D landing? I'm not sure I follow the question. In three-dimension space. Well, I haven't tried, the lunar lander is a 2D dimensional environment. I haven't tried it in 3D dimensional, but I think it will work brilliantly. I think the 2D dimension, the 3D dimension will work as good as the 2D dimension. I haven't tried it. I haven't thought about it, actually, to tell the truth.
Okay. Second question regarding the IPP. What is causing the IPP to be better than MBGP, but such a large gap, by such a large gap?
Oh, well, that is the use of the teacher model, which is its use is important because it has 2 main parts that needs to be addressed. First of all is the transfer learning part using the policy distillation, which is a big part, and it also helps to stabilize the process. As we already saw in the tables, KDBP also uses a variation of the policy distillation and also outperforms the magnitude-based gradual pruning. But another point here that IPP does that MBGP doesn't, other than the transfer learning, is the important part that the experiences that the model is trained on is fed by the teacher model, which already has a trained policy, and that actually cuts the need for the pruned model to perform exploration. And that is the main point in the IPP that is able to stabilize the pruning process and make the compressing algorithms in the reinforcement learning domain a lot more stable.
Okay, very well. And one last question. So if I wanted to train a model with the same architecture as the compact model using traditional DRL methods, will I be able to train the model to solve the environment?
That's a big question because I can't really answer no, because I tried doing that. I failed using the same architecture with 66 parameters and training the lunar lander. I tried for like a week with multiple approaches, and I failed to actually solve the environment using traditional reinforcement learning methods. So my answer is no. But it's not a definite no, because there are endless approaches and possibilities. But I believe it will be a lot more simpler to train a large and redundant model to solve the lunar lander in 2D or 3D or any other environment or any other decision-making task, and then use PoPS in order to compress that model. It will be a lot more simpler because PoPS, you just push a button and it's good to go. You don't need to do anything. Just need to insert the teacher model and that's it.
Okay, thank you, Dor. I wish to remind you that tinyML Talks sponsors are ARM, a tinyML strategic partner, DeepLight, Edge Impulse, Maxim Integrated, Kixo, Reality AI, Sisense. Additional sponsorship are available. Please contact Betty at tinyML. ARM, the software and hardware foundation for tinyML. DeepLight, we use AI to make other faster, smaller, and more power efficient. Edge Impulse, tinyML for all developers. Maxim Integrated, the new Max 78000 implements AI inference at over 100 times lower energy than other embedded options. Now the Edge can see and hear like never before. Kixo AutoML for embedded AI, automated machine learning platforms that build tinyML solutions for the Edge using sensor data. And Reality AI is for building products. Sisense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. The next tinyML talk is scheduled for December 22nd by John Edwards from Sigma Numerics Limited, who will be talking about low MIPS and memory machine learning industrial vibration monitoring solution. Thank you all for joining this talk, and see you in the next talk.